Kia ora and welcome to Workshop 6. So today we're looking at neural networks, and so we're going to be using the same data as Workshop 4 and 5 on the computer performance, just so that we can compare back to those. So you'll recall that we have a number of predictors, about 21 I think, and a target variable user that we're going to be predicting. And we're going to be using a very simple neural networks here. We're going to be using single layer feed forward neural nets. So it's not deep learning. So deep learning typically does tend to use something like a neural network. There's various types that you can use, but will typically have multiple hidden layers. So that's why they're called deep. And the idea then is that those hidden layers act essentially as derived features. So hopefully they're picking out particular things in the data that you might not be able to see directly on the predictor. So for example, in image classification, you have a large image which is represented by a bunch of pixels and the colors for each pixel. And often, a single pixel isn't telling you much, but combinations of neighboring pixels may tell you things. Okay, so that's what the derived features are hoping to pick up in that example. So we're going to be using very simple neural networks that just have a single set of derived features, but nonetheless, even just with one layer of derived features, things are extremely flexible. And so we'll see as we go through today that we'll get the situation where we can essentially massively overfit the training data without any issue whatsoever. Okay, so we're going to start by loading our various packages. So we're going to be using the MNet package for neural nets, plus all our other ones that we know and love. We're going to be loading recipes as well, so that we can process the data, and we'll see why we have to do that later on. And we're going to set the initial seed, and we're going to split our comp data into two sets: a training set, which we're going to use for building our models, and then a separate test set that we're going to be using for evaluating our model. So you remember this is an artificial test set where we actually know the outcome. So a true test set, we wouldn't actually have the user variable in it, and of course our goal would be to predict the user variable on that set. So this is an artificial test set in that we're going to treat it as if it doesn't have the user variable in it, and then we're going to use the user variable in it to assess how well our model is fit. So we're going to start by fitting a neural network, and you'll recall that a neural network will have two things required of it. First of all, we need to set linearity equals true. That's because neural nets can be used for both classification and for prediction. So classification is just essentially prediction, where your outcome variable is a grouping variable. And when it is set to that, the outcome is typically the probability of each class. And to get to probability, you want that on the range 0, 1. So you want to transform the final linear predictor, which relates your derived features, your internal hidden layer, to the outcome. You want that linear predictor, the outcome from it, to be on the scale 0, 1. So by default, MNet will transform the output to be between 0 and 1 using a sigmoid function, just like it transforms the linear predictors of the input variables for each of the internal derived features. Now we don't want that to happen in this case because our outcome variable isn't on the range 0 to 1, okay, which will typically be the case for a prediction problem. So you want linearity equals true. The other thing that we need to specify is how many nodes or derived features we want in that hidden layer. And a rule of thumb for that is the number of predictors divided by 2 rounded up. Okay, so in this case we've got 21 predictors. They're all numeric, so each of them just count once. You remember if we have grouping variables, then we'd count the number of indicator variables that we replace that grouping variable with. So for example, if you had a grouping variable with 5 groups, it would contribute 4 predictors. Right, so we've got 21 numeric predictors, so we're going to divide that by 2 and round up, and so I've specified size as 11. And this greatly affects the model. So if you're going to tune something, this is what to tune. Okay. Now, you'll remember that when we fit neural networks, then what it does is, because we've got so much flexibility here, there's a huge number of parameters. In this case, there'd be, so you're going to have 22 parameters for each of the 11 internal nodes, right? Because you're relating the 21 predictors plus a bias term or an intercept term, so 22, to each of the 11. So that's 22 times 11, which is 242. And then we're also going to have a linear predictor relating these 11 derived features to the outcome, which is going to have another 12. So all up, we're going to have 254 parameters. So that's a lot of parameters to estimate from a data set that's only 600 observations long. Right? Our N is 600 and our P is 254. So we're not going to have a whole lot of data here to get sort of to a global optimum. And so what we do when we're fitting a neural network is we randomly select initial starting points for those parameters. They're often called weights. And then we basically use the backpropagation algorithm to tune those weights. So to move through the space of weights, so that 254 dimensional space, in order to find the optimal set of weights that minimize the residual sum of squares. So to make that process reproducible, because there's a randomization at the start, random choosing the weights, I've set the random seed. So the purpose of setting the random seed here is just so that this is reproducible. Okay. Now, it does mean that the model output that I get is dependent on that seed. So if I'd chosen a different one, I may well get a different answer. So it's just something to keep in mind. Like with random forests, the randomization means that each time you run it, you get a slightly different set of trees, and therefore a slightly different forest, and therefore slightly different predictions. And you don't want your decision based on, is this forest better than another one based on that random seed, because it's just random, right? You want to have some deterministic reason for selecting one model over another. So you've got the same thing going on here. So in practice, you would run this multiple times with different starting seeds to ensure that you're not you're not making a decision on which model to use, for example, which size parameter to use or which model type to use based purely on luck. Okay, so we're going to run this. You can see that we have 254 weights. We computed that correctly. And you can see that it converged extremely fast. So it only took somewhere between 10 and 20 iterations. In fact, probably only 11 or so if you compare these values. And it started off with the residual sum of squares very high, and then it reduced it down. But it converges very, very quickly, and that is a little bit of a warning. So either we got very lucky with where we started, and we found a good minimum, or we got very unlucky where we started, and we've sort of gone down and found a valley, if you like, on the residual sum of squares surface, and we've got stuck there, and we haven't actually gone any further. And we don't know which case is which. I guess we could run it a few times to get a sense. So let's run it again without running the set seed line. And you can see that I'm getting kind of pretty similar sort of convergence. It's converging very, very quickly. Okay. And we'll see why that is as we go through. Okay, so let's do some predictions from this model. Let's rerun it. So I got the initial one with the same seed, so you get the same results. And let's put another code chunk in here and do predictions. So we're going to do predict on on our model. And with our new data is going to be comp test. So you can see here that this outputs a matrix. So you notice that it's got this notation here where it's indicating that it's got both rows and columns. So this is the column 1. And you can see that the predictions are particularly poor and that every single observation is given the same number. This is another hint that our model is very, very bad. Okay. Now, because it's a matrix, we're going to have to convert it to numeric first. So there we go. That's a numeric vector now. And then we're going to bind it to comp test. and then we can pull out our user variable and our prediction and then everything else, just so that we can see them next to each other. And we can see, of course, that our prediction is very, very poor because we're given the same number. Oh, actually different numbers. Look at that. There's a different one. I didn't spot that before. And then we could compute MSE, of course. So we could do a summarize. MSE is going to be the mean user minus dot pred squared. Oops, got to get the square in the right place, don't I? There we go. So we get an extremely poor mean square error. You remember our mean square error from our linear model was on the order of 7 or so. Okay, so now we're going to mess about a little bit, and we're going to try and control the fitting a little. So we're going to grab our previous model. We're going to use the same random seed just so that we're eliminating the initial weight values, and we're just assessing whether the decay parameter changes things. So you remember that the decay parameter is essentially controlling how fast we move from each position in the backpropagation algorithm. So essentially what you do with a neural net is you initialize your weights. That puts you somewhere in weight space, if you like, that 254 dimensional space. And then what you do is you use the local information about the shape of the residual sum of squares surface at that point to figure out where to move. And so you do that by progressively differentiating the formula for the residual sum of squares. And because a neural net is essentially made via function composition, so you apply a linear function, a linear model to the input parameters, and then you apply a sigmoid function to the output from that, and then you apply another linear model. So it's basically 3 functions applied one after another. Because of that, you can use the chain rule to do the differentiation and therefore figure out which direction you need to move each of the weights in order to best reduce the residual sum of squares. Now, when you do that, you need to decide, once you've determined which direction you need to go, you need to decide how far to go, so how much to step in that direction in order to move down the hill that you're on, basically, into the valley, which will minimize the residual sum of squares. And that's what the decay parameter controls. So it's basically controlling how far you step. So let's run that. You can see that it sort of starts settling down to the exact same place, but then it makes a jump and gets better. And in fact, you can see that it stopped after 100 iterations, and we might be able to actually do even better here by increasing the number of iterations. And you can do that with max_it, which we might set to say 500 in order to go a little bit further. We'll rerun it. And now you can see that it's all of a sudden got a much better fit. And so this is, we'll see later, is mostly luck. Perhaps 1,000 iterations. And eventually it's converged. So there we go. Okay. So one thing to remember is that you should go as far as convergence, or at least you should go reasonably far. It's probably not going to matter if we stopped a little bit earlier. So if we'd stopped it at 500, you can see that the residual sum of squares is 1949, and we got it down to 1901. And there's not a vast difference between those, so there's probably not that much point in going all that much further. But nonetheless, it is more optimal. Now, the danger with going too far is that you're fitting too well to the training data, and therefore you will generalize to the test data not so well, potentially. Okay. So there's our fit. We're going to call this model 2. We've just overwritten model 1, haven't we? So let's rerun our model 1 code. So there's our model 2. And we can then do our mean square error, right? So we're going to take our comp test data. We're going to bind rows. Bind columns. And we're going to say predict equals predict on model 2, with our new data being our comp test. And then we're going to convert that to numeric. There we go, and then we can again select out our user and .pred just so that we can have a look at them. So there they are there. So you can see that I do have different predictions for each observation, so that's good. This is probably going to be a better fit, and then we could compute the mean square error. Okay, and we do quite a bit better. So this is comparable to the linear model fit that we had. Now it turns out that this just happens to be luck based on our decay. So choosing a decay like this, it just so happens that we've taken just the right amount of step in order to get out of a problem that we were in. Okay, but we don't know at this point that we're in this problem. So we'll see how that happens a little bit later. So now we're going to fit the same model using Parsnip. So you remember we covered the tidy models framework last time. And so we're going to use this using MLP. So multi-layer perceptron. We're going to be using it in regression mode, and the engine is going to be nnet, so that's the package that we're fitting it with. And we're going to be using 11 hidden units. And our decay term is now penalty. So you remember Parsnip, Parsnip is all about providing a consistent interface to multiple different engines for doing the same thing. So in this case, there's multiple different packages that we can use within nnet. If we have a look at the help for MLP, we can see that we've got nnet, Brule, H2O, and Keras are all different ways of fitting multi-layer perceptron models. And so because you've got all these different models, then they are all going to use different interfaces, right? So nnet we know uses a formula syntax and has parameters that are called size and decay and maxit, right? Whereas some of these other ones might have equivalent parameters for these things, but they might be called different things. Perhaps they may not use a formula syntax. They might use a model matrix or something, right? So the purpose of Parsnip is to, and tidy models in general, is to unify that framework so that we don't have to care what the engine is. We can swap the engine out and use the same code, and it will give us the same thing. All right. So after that, of course, we do our fit. So we take we do our fit with user in terms of everything and our data is comp train. All right, so this is going to be, what am I calling it, model 3? Yes. So there's our model fit. And then, so I could have a look at it. So you can see that it's a Parsnip model object. It's got 254 weights. Now those are all its inputs and so on. Its decay was 0.001, and we've got linear output units. So notice that I didn't have to specify linearity equals true here, because MLP knows that if you've got regression mode, then you need that anyway. So it sets that up automatically for us, which is kind of nice, right? Now, one thing we don't know is whether this has reached convergence or not, and we could find that out by grabbing out the fit engine. Right, so now we just have the nnet object, and then if we have a look at the help for nnet, let's get the help for nnet. Then we can see, if we read the output contains, it contains this variable convergence. So convergence is set to 1 if the maximum number of iterations was reached, otherwise it's set to 0. Okay, so what we can do is we can grab our fit engine and then we can pull out the convergence parameter from that. And one way to do that is with the pluck function. So this is for pulling a particular named object out, or named component out of a list. So a little bit of backstory. Essentially, all objects in R, or all objects that are sort of more than just a numeric vector or a matrix, are lists. So for example, data frames are lists. So that's the underlying data structure. And lists then have essentially slots inside them, if you like, or values that they can take. So this is typically objects in R are a named list. So each of the components inside that list will have names. So a list, if you like, is like an array, except the items that can be in it can be anything. So they don't all have to be the same type, right? So technically an array in most computing languages is a series of the same object type, whereas a list is a series of different object types in R. Okay, so we can put whatever we like into a list. And so the pluck function is a function for pulling things out within lists. In fact, it's within nested lists, pluck can do. So you can sort of go explore the full depth. So because a list can contain anything you like, you can put a list within a list, within a list, within a list, and so on, and therefore construct hierarchies and so on. And many objects are constructed in that hierarchical way in R. So the pluck function is a convenience function for pulling out the convergence object. So I'll show you another way to do that in a moment. But you can see here when we pull it out, we have the value 1, which means that the maximum number of iterations was reached. So we haven't reached convergence here. Instead, we've hit the maximum number of iterations. Now, the other way to look at this is to actually pull the object out itself. So if we run extract fit engine, and then save that object, so we could say innet object. Right, so now you can see the innet object is a list of size 7, and then inside it you've got a bunch of stuff. So you've got an args argument, which itself is a list. So that's the arguments that was passed into the innet function. So you can see that the hidden units were set to 11, the penalty was set to 0.01, and so on and so forth. Oh, sorry, that's spec innet objects, a list of size 18. So we've got all of these things. So you can see here's the decay parameter, 0.01. These are the initial weights. These are the convergence thing. And you can pull those out using the dollar. So the way to access objects in a list is to use a dollar if they're named. So we could look at dollar convergence. So there it is there. Or we can use double brackets to look in lists. So to get the first thing from the list, you use double bracket 1, which will be the first thing in the list, which is this n thing here. So n in this case is the number of nodes in each layer. Right, so we've got 21 in the first layer, 11 in the second, that's the hidden layer, and 1 in the output. Right, so we could use 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So if we pull out the 12th entry there, we'll get convergence. Okay, and we can also reference by the name of the... Okay, so that's just a little bit about the objects that make up R, if you're interested. Okay, so the tidyverse way of pulling things out is pluck, because then it works with all your pipes. Okay, so we haven't converged, so we really should add another parameter to the MLP to ensure we get convergence. And if we look at the help for MLP, we see that we've got this parameter epochs, an integer for the number of training iterations. So we might want to go epochs equals 1,000. Right, so now when we rerun this, we see that our convergence is set to 0, and a 0 means it's converged. Okay, so now we can do our usual fitting. So we can go, we can grab our neural net fit, and we can then augment that. We could use predict if we wanted to. New data is a comp test. So there we go there. So there we have the .pred and then we could use metrics to compute our metrics. So the truth is the user variable and the estimate is our predict. So there you can see here that we're getting 2.76 for the root mean square error, and that of course is just the square root of 7.62. Okay, we get the exact same model fit with the Tidy Models framework than we do with the old school setup. The advantage, of course, is this is then taking care of the fact that if we wanted to replace this engine with something else, we could just swap it out. Okay. Now, the bits that might not swap out would be the stuff here. Okay, because you'd have a different fit engine, and so you'd have different objects within that fit engine, and so that would then be specific to that engine. Okay. Right. Now, one thing we noticed when we fit the initial model is that we got a very poor model fit. It converged extremely quickly. And the reason for that is that we've hit a numerical fault. And of course, there's no hint that we've hit in a numerical fault, but that's what's happened. And the reason is that all our variables are very large in magnitude, or some of them are very large in magnitude. So you can see that R char and W char are almost in the millions, whereas some of the others are very small. Okay, and so what's going to happen here? Here's a free swap very large as well. And so what's going to happen is when we you remember what happens at the start is we randomly initialize the weights, which are the coefficients of the linear model bits of the neural net. So at the first step, we would be taking a linear combination of all these things with random weights. And if the random weight that we chose for R char or W char was sufficiently away from 0, and it doesn't have to be far away from 0, the outcome is going to be a very large number. Right? It's going to be, from the linear predictor, might be in the millions. Okay? And then you'll remember that that is then exponentiated in the sigmoid function before we hit, so that's the transformation that's applied in order to get to the values in the hidden layer, the z's, the derived features. And when you exponentiate 2.4 million in a computer, you get infinity. Right? The computer can't represent that number. It can go as high as about 2 to the power of 300 odd in 64-bit double point notation. Even in 128-bit double point notation, it can only go so far, right? And so what's happening here is that once you've done that exponentiation, you get essentially infinity, and then once you've finished doing the computation for the sigmoid, you get exactly 1 or exactly 0. Now the problem with that is that even if we move the weights a little bit, we take a step, we work out all our derivatives and so on, and then we take a step in the right direction to try and reduce the residual sum of squares, the weights are likely not to move too much, and so you're going to have a very similar value for your linear predictor, which again, once exponentiated and applied the sigmoid, is going to give you again identically 0 or identically 1. And so the algorithm is going to see that and say, well, I took a step, but nothing changed. I'm still at 1 for these parameters, and I'm still at 0 for these other parameters, and so I've converged. Right? And the reason it thinks it's converged is that there's just not enough precision in the computer in order to distinguish the fact that these two numbers are actually different. I've taken a step. My linear predictor might have changed actually quite a bit. I might have gone from 1 million down to 10,000 or something, right? But 10,000 is too big for it to represent in the computer as well, and so it can't see the difference between those. It just sees infinite in both cases, and therefore when you do the sigmoid, you just see 1 in both cases. So it looks as though you haven't moved when in fact you have. And so it thinks it's reached convergence when of course it hasn't. Okay? And so what we need to do is we need to scale the data down so that this problem of hitting essentially sort of running out of precision in the computer doesn't happen, or is much less likely to happen. And so one way to do that is to just do a linear transformation of all these things. Now that shouldn't alter our model fit at all, right? Because we're then taking a linear combination of all these things to get to the hidden layer, right? And if we just do two linear functions in a row, we just get another linear function, right? That's the whole thing with linear transformations. So this shouldn't change anything, yet we'll see it does. And the reason, of course, is that the original model that we were fitting, that converged in like 11 iterations, wasn't actually converged at all. And that when we take those comparable steps just by scaling everything down, we'll find that, in fact, we can do better. Or worse, we'll find out. So one way to do this is sort of an old school base R. I've pipified it, but essentially it's the same thing, is to use some functions to work out the... so essentially what we want to do is we want to take the columns here and we want to subtract out the mean so that we shift them to mean 0. And then we want to divide by the standard deviation, so we shift them so that the scale of the variables are comparable. So to do that, we first have to compute the mean and the standard deviation for each column, which can be done with the apply function. So if I run this block, you'll see that comp train mean, do we have that? Is let's just spit it out so we can have a look at it. So comp train mean is just a vector of the mean of each of those columns, and then comp train SD is the standard deviation, okay? And then we're going to use those two things. So we're going to use the scale function to take all our training data except the user variable and scale them all by those means and standard deviations. Now the problem with this is that scale runs on outputs a matrix, and we want a data frame, so we've got to convert it to a data frame, and then we've got to bind it all back and add the user variable back in. Right, but nonetheless you can see what we've done. Right, if we have a look at comp train scale, and we perhaps skim it. We haven't loaded the skimr package. Then you can see that all of them have extremely low mean, except for the user variable, which we haven't scaled. All of them have essentially 0 mean. Right, this is 10 to the minus 18. That's a very tiny number, and 1 standard deviation. So we've scaled them all to be to be similar, whereas our previous unscaled data, had vastly different means and standard deviations, right? Now you can do the same thing yourself in the tidyverse with dplyr, and the trick is to pivot longer. So what we need to do is we need to apply the mean function and the SD function, right, to compute the mean and the standard deviation to every column. And so a simple trick is to pivot all those columns longer, right, and then group by the column name. Then we can compute the mean once and the standard deviation once, right, because we're just computing on the column, on the value column, if you like, by group, right? So if we run this, then we can see that we've got some scaling data, which is now each variable name, the mean, and the standard deviation. So now when we've got this, we can use this again with a pivoted longer version of our data frame to do the scaling. Okay, so this is a common trick when you're trying to do things across multiple columns at once. You can do it by pivoting longer so that all those columns end up into a single column, grouping by the column name so that everything is per column essentially, and then doing the computation once. So it's similar to how we did the scatter plots, the bivariate scatter plots of user versus all the variables, right? in order to get that all done within a single chart with faceting, we pivoted all of the columns that we wanted to put on the x-axis long. We made the data untidy in order to feed it all into ggplot with just those two variables, the user variable and the value variable for the two axes x and y. So now let's see how we're going to do it. We're going to pivot the data longer. So let's perhaps I'll just put that on another line so we can see how it works. Right, so we're going to pivot the data longer after adding a row ID. Right, we're adding a row ID so that we know which observations belong to each other when we pivot back wider at the end, because we want normal data at the end to feed into the neural network. But now that it's long, we've got our name variable there, and we can join to this data set here so that we get the mean and the standard deviation of each variable alongside. Right, so this is what the left join is going to do. Let's have a look at that. So now you can see I have the same data. I've got my row observation here. And then for LRead, I have the corresponding mean and standard deviation. Now I could also do this with a mutate, right? I could have pivoted wider, grouped by name, and then did the mean with a mutate and the standard deviation with a mutate, which would have added them as columns, and I would have been here directly instead of having to do the join. Okay, so I could have done code that looks a bit like this. So I could have taken my train, pivoted longer, and then did a mutate, grouped by name, so that everything's done per column, and then mutate mean equals mean of the value column, and SD equals SD of the value column. Right, they could have done the same thing. I've got the same answer there that I do have there. Okay, so once I've got that, I'm then going to group by name, and then I'm going to compute the scaled value. Right, so the scaled value is going to be, let's get rid of this so you can see what's happening. So I'm going to take the value column and I'm going to subtract the mean and divide by the standard deviation. Right, now I don't need the mean and standard deviation columns anymore, so I could do, so if I have a look at the help for mutate, then I've got this keep parameter. And if you have a look at what the keep parameter does, control which columns from data are retained in the output. Grouping columns are always kept. So all retains all columns. This is the default. That's not what we want. Used retains only the columns used to create new columns. That's not what we want, because we don't want to ensure we don't want the mean or SD variable anymore. Unused retains only the columns not used to create new columns. That's what we want, I think. Right, so this is an alternate to using select to get rid of them. So there we go. Okay, so now we've got our scaled value, and now of course we can pivot that back wider, get rid of the row ID, and there's our final data. So the alternate would have been the same thing. We're already grouped by name, so we can do the computation directly. In fact, we could have done it in one, couldn't we? We don't need the mean because we can just compute the mean. We don't need the standard deviation because we could just compute it. It's much simpler. And then we don't need to keep unused because we never create them. Right, there we go. Okay, so we're going to call that comp train scale. Okay, and we could check that it's the same as this one. So we have comp train scale here. So let's run that and have a look at what it looks like. So that's what it looks like. Okay, and if we run it down here, we get the same thing. Okay, so now we can use the we can apply the same scaling to comp test. Now I know why I didn't do it this way. So the disadvantage of this method is we don't have the mean of the value column and the standard deviation of the value column for each column name. With this method, we do, because we've got them in comp train scaling. Right, so I need to scale the test data by these exact values because I need to make sure that whatever transformation I apply to the training data is applied the exact same way to the test data. So that's why I did it this way, rather than the smaller method. So I'm going to have to use this method here. So we'll just write a note here. And I'm just going to comment it out so that it's clear that you shouldn't do it. Okay, so we've got the amount that we want to scale. So what we're going to do is we're going to create a new data set. We're going to take our test data and we're just going to rerun everything exactly the same. Okay, so we're going to add our row identifier. We're going to pivot longer so we get our name and value column. We're going to left join to our scaling data so we get the mean and standard deviation that we computed off the training set. And then we're going to apply those to the test set. And so we get our test set scaling. So we'll call that comp test scaled. Okay, fit another neural net. So what we're going to do, what number model are we up to now? 4? 4. Let's just grab this code here. I think the spec's not going to be the same. So we're going to have a spec where we're not going to specify the number of epochs or the penalty, so that we get the same spec that we had in the initial model, right, where we didn't specify the decay rate. And you'll remember that model converged extremely quickly. We can check that here, right? So if we run model 4.nnet, then if we extract the fit engine, we can see that it's converged, right? And it's converged after just those 11 steps, 11 epochs or iterations. So now we're going to test it to the, we're going to fit it to the scale data. And then from our, and then we're going to do our prediction on our scale test data. So let's see what happens now. So we fit our model and we see that we do not reach convergence. So exact same setup. All we've done is scaled the data and now we have a different result. Now that shouldn't happen in anything that uses linear models under the hood, right? Because the underlying linear model engine, the underlying linear model, if we scale the input parameters, all we end up doing is scaling the weights in the end. But of course, that's enough here to get us out of that situation where we'd reached an artificial point of convergence. So now we're going to see that we're going to need more epochs. So we can maybe try 500. See if that'll converge. No, still hasn't converged. Let's try 1,000. It still hasn't converged after 1,000. Now I'm getting a little bit worried that we're hitting another problem, but let's keep going, see what happens. Let's try 5,000 epochs. Computers are fast, doesn't really matter. Still haven't reached convergence. Let's try 10,000. Now, I wonder whether I'm actually setting this incorrectly. Let's have a look. No, it is epochs. I'm not using the... That's the problem. I'm using the wrong spec. Let's go back. Right. Okay, we definitely don't have convergence. That's good, because that's what I was claiming before. Let's keep going. 500. Still not converging. 1,000. Still not converging. 5,000. Okay, so we've hit convergence. Hooray. But it took an awfully long time. And my worry here is that when it takes a long time, it's often overfitting. But let's see what happens. Let's get rid of that there. Let's do our... Perhaps what we might do is we might have a look at the training fit. Well, first we'll do the test fit, as per usual, to see what's happening. Right, so we've got doing it on the scale, and we can see that we have an extremely poor fit. Right, so while I said up here it should perform rather better than the unscaled ones, in fact it does not. It performs substantially worse. So what might be happening here? Well, let's have a look. My guess is that we actually have a very poor fit. Let's have a look at the plot of our fit. Right, everything should be along the line, right? If I do slope equals 1, right, everything should be along the line, but you can see that 3 of the predictions are extremely poor, and a few of the 2 are pretty bad. In fact, that we're predicting a user variable well over 100, which it should never be, because this is the percentage of time the CPUs are available in user mode. It should never be 200. So we've done extremely poorly at some of these observations. And my guess is what's happened is we have overfit to the training data. So let's grab the training data. Yeah, so you can see that we're fitting that very well indeed. Okay. So, while we haven't hit the numeric issue that we had at the start, we have hit a different issue in that we're now overfitting to the training data. Now, we may not get that if we set a different random seed. So let's try that. We might still, because we've got a highly flexible model, but let's see. So let's rerun it with a different seed. We can see we've reached convergence, and we get a much better root mean square error. It's still not very good though, is it? My guess is we've still got the same problem. Yes, but it's not as bad. Okay, but we've still got overfitting. So the problem here is that we're just fitting a model here that is too flexible to these data. Okay, and we're allowing it to sort of zoom in on the fit. And so probably a better thing to do is to play around with a number of hidden units and perhaps reduce some of the flexibility, and that might help. You remember that a lot of this, that this data set is particularly good with a linear model, right? Because a lot of the relationships between the user variable and the inputs are linear, right? So you don't need the hidden layer a lot of the time. And so by having a whole heap of derived features in there, you're essentially sort of enforcing non-linearity, which is not really actually required in this case. Okay. All right, let's just rerun that so we have our... Okay. Now, we're going to finish by seeing how we can better do this scaling, because this is rather cumbersome. And of course, there's a package for that. There's always a package for that. And so we're going to construct a recipe with the recipes package. And the recipe is just going to be to normalize all numeric predictors. Right? So the recipe starts with a template for your data. So the template is most easily filled in by specifying a formula so that it knows what the outcome variable is, and a data set so that it knows how many predictors it has. So this is just for naming predictors. That's all that does. And then we add a step to do the normalization. And so you can see that it's now saying it's got centering and scaling for all numeric predictors, and it's got one outcome variable and 21 predictors. Now the recipe just describes the process. You've then got to train the process, right? In particular, we've got to determine what are the coefficients for the normalization. So what is the mean that I should be subtracting by, and what is the standard deviation I should be dividing by? And we do that by preparing our recipe. So we take our recipe, we run the prep object on it, and we feed it a set of data so that it can derive those things. So you can see here that it says that it's trained the centering and scaling for all those variables on 600 data points that had no missing data. And so now we're ready to go. So now that we've trained it, essentially the recipe now holds which functions it needs to apply to a data set in order to do the transformations that we want. And it also knows exactly what the transformation should be. So what should it add and subtract to each variable in order to get to the scaled variables. Now we haven't actually processed that, we haven't actually applied that to a data set. Our comp train is still the same as what it always was. So now we use bake in order to bake our final data set into the final product. So here we're taking our trained recipe and we're running the bake argument on our training data, right, which will apply those steps that we set up in the recipe to the training data to give a scaled version. So you can see comp train. So we'll run both of those, and then we'll maybe do a skim. Right, and you can see that again, this has standard deviation 1 and mean 0, except for the outcome variable, which is untouched. And in fact, this is the exact same scaling as we got before. We could check that with an anti-join. And of course, if it's the same, it should return no rows. You remember an anti-join returns rows in the training baked data that aren't in the training scale data. It's returned no rows, so they are identical. Okay, so our steps in this recipe are, so the steps to set up the scaling are to configure a recipe that defines the scaling. You then prep it using the training data. You then bake it on both the training and the test data, and then you fit your model on your baked data. Okay, so these are the steps. So you use recipe to set up the process for the data. You prep it to the training data. You then create your model specification. You fit the model with the baked data. You predict the model with the baked test data, and then you evaluate your model metrics in the usual way. So here's the sort of process. We're going to create a recipe. We're going to define the transformations that we'd like to have on any data set that we apply, and then we're going to train those transformations with the training data. Right, we're then going to create our model specification. We're then going to fit it using the baked training data. Right, so we run bake on the training data, and that's what goes into the model fit. And then when we do our prediction, we run bake on the test data. We could alternatively do this with augment. Right, we could just go is NNFit augment new data equals bake. Right, same thing. Oh, we've got to run the whole thing. Okay, and then we get our metrics at the end. Now, each time we run this, of course, we're going to get different answers because we haven't set the random seed. Okay, so you can see that sometimes the answers are very bad and sometimes they're okay. So we could check that we're reaching convergence. So we'd extract the fit engine. And then we could pluck convergence parameter. No, we're not. Right, so we should change the number of epochs so that we go a bit further. And now we're reaching convergence and we've got a better model fit. Okay, again, each time I run it, of course, I'm going to get a different answer because I start off with different weights. But at least now the answers that I'm getting aren't too wildly poor. I'm not always reaching convergence, so I might want to give a few more epochs. Let's give it 10,000. There we go, we're reaching convergence. Now, again, each time I run it, I'm going to get different results because I've got random weights. But hopefully they shouldn't be too much different if we are in fact converging to a similar spot each time. They're still bumping around a little bit. So we might want to add a few notes here. So as the initial weights. Okay. And so the last part here is a prediction competition. So I'm not going to do anything. This is for you to have a go at. So we've got a set of training data here. Okay, this is going to be similar in format to what you might see in your first assignment. Okay, where we've got a set of training data that has a bunch of variables and an outcome variable here, which is the rejection variable, rejection probability. So this is about banks, and so we've got a bunch of information about the bank, queue size, and so on. And the goal is to build a model for the rejection variable. So the goal is to predict the rejection variable. And we also have a test set, and this is a true test set in that if we have a look at it, we don't have the outcome variable. So we don't know what the rejection is for this set. And your goal is to use the training set, these 7,000 observations that you have, so you've got plenty of data, to train up a bunch of models for the rejection variable. And then once you've determined your best model using that training data, the idea is that you're going to do a prediction on the Bank Predict Me data set and see how well you do. So send your prediction to me. I will then assess your prediction. I do have the same data set here, but with the outcome variable. So I do know what the truth is, the true rejection variable is for each of these, and therefore I can evaluate how close you get to the truth using mean square error, for example. Your goal should be to split the training data that you have here, the 7,000 rows, into two sets so that you have a separate artificial test set or a validation set in order to determine which variable you want. Now, some notes are that these variables are already pre-scaled, so you shouldn't have to use a recipe. The exception is the Q variable. You're welcome to assess whether you need to scale that or not. My guess is you don't, purely in terms of the numeric considerations for a neural network, because this isn't too large in magnitude, right? So train a bunch of different models, assess them on your artificial test set that you generate, determine the best model. Once you've determined your best model, retrain it on all the data, so all 7,000 rows, so you can use everything you have, and then predict on the bank data, on the Predict Me data. Once you've got that, save it to a CSV file, e.g. using the write CSV function, email it to me, I'll see how well you do, and perhaps I might do it as well and see how well I can do. And we'll see what happens. So enjoy.